Okay, so we are going to talk about the first section of chapter 17, which is the last chapter of a chemical equilibrium. Remember, we have gone through 2 chapters of equilibrium already. The chapter 15 is about an overview of an equilibrium. And so we make this very specific in chapter 16, which is acid base equilibrium. And now we're going to use our knowledge of acid base equilibrium to explain some of the applications of this equilibrium that we're going to see in, for example, in our real life. So what is the chemistry going on inside of a body, like a body fluid, and some of the chemical problems. So for example, why are so many rocks? Okay, why we have so many ionic compounds that does not dissolve in the water? Okay, so in order to answer all of this, first we need to understand one of the effect that we call the common ion effect. Before we talk a little bit more about the common ion effect, first let's take a look at this weak acid dissociation. So say if we have 0.1 mole of acetic acid dissolving in water, and then it dissociates and it gives up the acetate and hydronium, and we understand the Ka is equal to 1.8 times 10 to the negative fifth. Okay, so we noticed that this is the initial concentration of acetic acid. We know what the Ka is. If a question wants us to solve the equilibrium concentration, so everybody understand that we're going to set up an ice table. So after we set up an ice table, that we get it solved, so we can actually figure out the equilibrium concentration for all the species in this equilibrium. So for example, the equilibrium concentrations of acetic acetate, and hydronium as this follow. Not surprisingly, we do not see a lot of dissociation going on. Only a very small amount, I would like to say probably somewhere around 0.5% dissociated into this weak acid. So dissociated in this weak acid solution. So we only wound up with a 0.0013 molar of the cations and anions. Okay, so more than 99% of this acetic acid still remains as intact as the molecules. Well, you may wonder what happened. There's nothing new here. Okay, so this is something that we have been practicing in chapter 16. Now, I want you guys to understand. We're going to put this equilibrium into something different. Imagine we transfer this equilibrium into a 0.1 molar of sodium acetate solution. You may wonder why. Why sodium acetate? Why can't it be why it can't be some other salt solution? Because I just want to point out the sodium acetate, as we can see, you got CH3COO, which is a minus. Why minus? Because sodium is a plus charged. All right. And we recognize CH3COO minus is this anion. And this anion is what we called conjugated base, which is the conjugated base of what acid? This acid, conjugated acid. All right, so we didn't put this equilibrium into the salt solution that is not totally unrelated with this equilibrium. We put it into the equilibrium into a solution that has pretty high concentration of its conjugate. So once we realize this, things are going to change quite a bit, because now we realize, since this equilibrium has put it into another solution, and this solution contains a certain concentration of one of the anion or cation, if we talk about something else, as we'll see in our example. So if we put this into this conjugate, this equilibrium is broken. The old equilibrium is gone, and before a new equilibrium is about to establish, we can actually to find out just what kind of initial concentration for this new equilibrium which is about to establish. Well, since this entire equilibrium has been put into 0.1 molar of sodium acetate, and we understand sodium acetate is a soluble salt, and being a soluble salt, it is a strong electrolyte. When we talk about strong electrolyte, it leads 100% of dissociation. So that means 0.1 mole of sodium acetate leading 0.1 molar of acetate. So with that in mind, now the concentration of acetate has been changed to 0.1013 molar. So here I just make a simple addition to make a point here. So the concentration has been this much. Well, the new initial concentration of the other two, acetic acid and hydronium, will still remain the same from the old equilibrium. All right, so with this new initial concentration set up, before we conduct any more calculation, first thing we can do is calculate QC. So QC has the same math as KC, but QC is for initial concentration only. So we multiply initial concentration of the products divided by that of the reactant. We see the QC is 1.3 times 10 to the negative third. Remember, if we put the QC in the first place, followed by the Ka, and we realize Ka is smaller because QC is greater than Ka. So if we draw the arrow, we realize that the arrow is from right to the left. This arrow tells us which direction this equilibrium is going to shift. So we understand it's going to shift to the left. So this shifting of equilibrium is what we call the common ion effect. So the formal definition of common ion effect is a shift in an equilibrium on adding a substance that provides more of the ion that already in an equilibrium. This is one of the most important effects that we're going to see in this chapter. Because this common ion effect will lead one of the most important application of acid-base solution, which is a buffer. Buffer exists in any fluid in biological bodies, including cells. Even our urine is a buffer solution. Okay? So buffer solution actually can be derived from an effect we call a common ion effect. So what is the common ion effect? To the very bottom. It is an example of a Le Chatelier principle because, as we recognize, if we add more of the product, according to Le Chatelier's principle, equilibrium shifts to the direction that reduce this concentration of the acetate. So equilibrium shifts to the left. So common ion effect is an example of Le Chatelier's principle. But what is even more here is now by introducing a common ion, which is the conjugate. Okay? So by introducing the conjugate into an equilibrium, it could be a conjugated base for a weak acid or a conjugate acid for the weak base. It doesn't matter. The only here we use the conjugate, so we use the weak acid as the example, but it also applies to the weak base, which we'll see that in our example. So if we put a weak acid solution into a solution of its conjugate base, not only we see that it causes less dissociation of its weak acid because we understand equilibrium has a shift to the left. Shift to the left means there's going to be less dissociation of the acid. But what is even more is you realize there's H3O plus here. If equilibrium shifts to the left, concentration of hydronium goes down. Right. So let me change that into a different color. So the concentration of hydronium goes down. What does that mean? It means the pH changes as a result. If pH changes, we changes acidity of the solution. That is the most powerful conclusion we can draw from this common ion effect. Okay, now, just how are we going to do the calculation that involve the common ion effect? First, I'd like you guys to realize what kind of keywords we are looking for this type of calculation. The keywords here is a pair of conjugate acid and base. That is the must for common ion effect. Most likely, the concentration of this pair of conjugates is provided. In a very rare case, I only saw that in my own personal experience as chemistry major student. Question asks for the concentration of one of the conjugate. But in our course, most likely, when we study or calculate the common ion effect calculation, the concentration of the pair of conjugates are usually given. So it is very important for us to realize we do see a pair of conjugates in that part of a calculation problem. That gives us the hint to realize this is the calculation about common ion effect. As for strategy, first we need to determine and highlight this pair of conjugates, which one is acid, which one is a base. And if concentrations of this conjugates are not given, say only provides grams or the moles or something, and we need to get them converted into the concentration. Remember, okay, we're going to set up ice table. For the ice table, it is the concentration that really counts. All right, so once we realize the concentration, we have realized this is a equilibrium problem, this is a common ion effect. Depending on which K is given, we write up a, like I said, corresponding dissociation equation. If Ka is given, we write acid dissociation. If Kb is given, we write a base dissociated equation. For acid dissociated equation, Ca, conjugate acid, must be the reactant. For base dissociated equation, conjugate base must be one of the reactant. The other reactant in either dissociation equation must be water. Then we figure out the rest. So that is very important for us to understand how to write dissociation equations. So that is something that we have emphasized in chapter 16. Remember that I put a big arrow and with the caption in it to say, okay, so how do we realize what the product is going to be for acid or base dissociation? Before we set up the ice table, first we need to know which direction this equilibrium is going to shift. It is not like acid or base dissociation equation. So the direction of the equilibrium always shifts to the product. But for the common ion effect, no. It could go reverse. So that is why we need to calculate the reaction quotient Q to determine which direction this equilibrium shifts so that we can add X to the product side of this equilibrium determined by the QC. All right, so once we set up the X as a change in concentration in the ice table, we finish the setup of the ice table, we conduct the calculation like we did in Chapter 16 before. And when it's all done, we just ballpark check the K with the equilibrium concentration we calculated to make sure our calculation is correct before we report the pH of this solution, of this new solution. Now, let's take a look at our first example of this chapter. This chapter has two questions. First, we need to calculate the pH as for comparison for a weak base solution. How do I know it's a weak base solution? Because it's ammonia. And Kb is provided. And for second question, to this weak base solution, 1.07 grams of ammonium chloride is added. Then we are asked to calculate the pH again under the assumption that there's no volume change. Remember, if a volume changes, concentration changes because concentration is equal to moles per liter. So it is very important for us to realize a certain assumption during the calculation. All right, let's look at the first question. So here I highlight the pH and the concentration of ammonia, 0.40 molar. And by now, I hope you realize what I'm trying to say here. pH is an equilibrium concentration, while the concentration of a base, ammonia, is an initial concentration. Since both concentrations are involved, one is given, one is desired, so we know that it's going to be a RAS method using ice table. All right, so we identify a pair of conjugates. So the base is ammonia, and it's for conjugate acid. We add one proton to it, so it becomes NH4+. Kb is given. We compare that against Kw to find out whether ammonia generates almost 100% of hydroxide. And we find out that that's true because Kb is much greater than Kw. So the dissociation of ammonia dominates the concentration of hydroxide. Then we write the base dissociation of ammonia. Ammonia here as a base, so we understand OH minus must be one of the product. Because solution is going to be basic, right? If a solution is basic, there has to be more hydroxide than hydronium. All right, so this is hydroxide is a base. Ammonia has to be one of the reactant. Dissociation, water is a second reactant. So we should be able to lay out the base dissociation of ammonia by ourselves. Okay. Now, with the initial concentration 0.40 and the 0 for the both of the product, so remember, we need to know which direction this equilibrium is going to shift. So let's calculate the Q. QC is equal to 0, and 0 is less than non-zero value, right, which is positive. So we understand the equilibrium shifts from right to the left, from small to the large, so right to the left. So it's now makes perfect sense for us to add plus X under the hydroxide. And we add a plus X under the ammonia using stoichiometry, and the minus X under the ammonia as well. Once we figure out the equilibrium concentration, and we can just solve this X using Kb. Okay, so we plugged it in, so it's X times X divided by 0.40 minus X equals to Kb, which is 1.8 times 10 to the 5th. Well, I hope that you have already finished the homework assignment about the weak acid, weak base, or salt. So I just assume that we have a very good experience about the 500 rules. So every time we see something like this, let's apply 500 rules. So initial concentration divided by Kb, we find out it's 22,222, which is much greater than 500. That means we can take off X from 0.40. Why? Because Kb is so small comparing to the initial concentration, so X is going to be very small. It won't affect basically the concentration of the base. All right, so after we take away this minus X from this equation, so the rest should be very easy to calculate. If we multiply 0.4 on both sides, take the square root, so we have X equals to 0.0027 molar. X, as we now know, is the equilibrium concentration of hydroxide, so we can calculate equilibrium concentration for all the species, or all the species we're interested in is equilibrium, like equilibrium concentration of ammonium, as well as equilibrium concentration of ammonia. As you can see, 0.0027 compared to 0.40 is virtually nothing, because that's beyond our sig figs. So even through this subtraction, if we round it up, we still have 0.40 molar. Before we going forward, let's check the Kb with our equilibrium concentrations. So Kb is a perfect match for the one that's given to us. So we can calculate the POH, because we know the equilibrium concentration of hydroxide, which is 2.57, the value of POH. And then we subtract this 2.57 from 14. That would be the concentration. So that would be the pH of the solution, 11.43. Quite basic. All right, so that is all for question A here. Now let's look at question B. As you may guess, question B is about the commonality effect. Of course it's commonality effect, because we understand that we got ammonium chloride. Ammonium chloride is a soluble salt, because all the ammonium salt is soluble. Since it's an ionic compound with ammonium and chloride, so it is a strong electrolyte. Being strong electrolyte, it's going to undergo 100% of dissociation. So as we can see, here is the single arrow, 100% dissociation. Since it's 100% dissociation, so we can actually calculate just how much of ammonium the solution is going to get introduced. All right, so we got 1.07 grams of ammonium chloride. And we are so using molar mass and divided by the volume. And we find out it's a 0.040 molar. And according to the dissociation equation, it's a 1-to-1 stoichiometry between the salt and ammonium. So we know for sure the concentration for ammonium is a 0.040. Remember from the previous question, question A, we have the equilibrium concentration for the weak base. As we put ammonium in, ammonium chloride, so introduce more ammonium, and this equilibrium is going to get disturbed. It's no longer the equilibrium, so we can use the equilibrium concentration from the old one as the initial for the other species like hydroxide and ammonia. But only this time, the concentration of ammonium NH4 plus has changed, because we introduced a 0.040 molar into it. So it's going to be 0.043 molar instead of a 0.0027 molar. Again, same base dissociation equation. Why we write a base dissociation equation? Because again, it is Kp that is given, right? If Kb is given, so we write a base dissociation equation regardless what the consequences are going to be later on. So this is something that we're going to write up based upon the information we're given, which is Kb is given. Okay. Now that we have the new initial concentrations of ammonium, and hydroxide, put them in places, carry out the calculation, we found that QC is a 0.00029. Kc, remember, Kc here is Kb, by the way, is a 10 to the negative fifth. This is a 10 to the negative fourth, 10 to the negative fifth. So QC is greater than Kc. And I'd like to remind you, we draw the arrow from small to the large. So equilibrium shifts to the left. So left actually is the product side of this new equilibrium here. All right. So now that we lay out the initial concentration, we understand the left-hand side is the product side of this new equilibrium. So we put a plus X on the ammonia. Minus X for ammonium and hydroxide based upon this stoichiometry. And we calculate the equilibrium concentration. And apply the Kb to it. So this is what we have. It looks like it is going to be quite complicated if we want to do the quadratic equation. But, you know, we can always check out the 500 rules for a minute. Because if you find out the 500 rule applies, then somewhere in this equation, it might just simplify the calculation a little bit. All right, so we have two initial concentration, actually it's three initial concentrations. So this is the initial concentration of hydroxide. This is the initial concentration of ammonium. This is the initial concentration of ammonia. So let's do 500 rules for two of these, right? So this one and this one. Okay, so if we divide those 0.40 by the Kb 1.8 times 10 to the negative fifth, we find out the value. If you recall, it's a 22,222. So that's much greater than 500. So 500 rule applies. If we go one more step by checking out the 0.043 to see whether they applies 500 rules, we find out it still applies this 500 rule. That means what? That means we can take X of both of these terms. We can take X of a 0.40 plus X. We can take X off from 0.043 minus X. That dramatically makes this calculation easier. Because we take away two X's, so that's a linear equation as you may see it. And carry out the calculation, we found X is equal to 0.00253 molar. Very small number. Of course, it's a very small number because if you look at what we got here, so the initial concentration of hydroxide is that much. All right, so let's calculate the equilibrium concentration of hydroxide. We find out we got the 3 zeros behind before it's non-zero digit, so that's a 0.00017 molar. And we carry out the rest of the calculation. So we got equilibrium concentration of ammonia and that of ammonium. Let's do the ballpark check. And we find out the new Kb here is 1.7 times 10 to the negative fifth. Remember, Kb is the 1.8 times 10 to the negative fifth, so that's not much of a difference there. So that demonstrates our calculation so far is correct. So that boosts our confidence to go on to calculate the pOH. So that's going to be 3.77. pH is going to be 10.23. If we compare this value against the pH we calculated from question A, which is 11.43, we find out pH is less, right? So as pH lowers, acidity increases. That means the less basic the solution becomes. Why? Why all of a sudden pH has changes? Of course, you can consider that as, all right, so this is a common ion effect, so equilibrium shifts to the left. Since it shifts to the left, then it decreases the concentration of hydroxide, so on and so forth. Yeah, that makes perfect sense. But there's another way for us to look at this. Let's look at this ammonium chloride. From our knowledge of the salt, we recognize ammonium chloride is a strong acid weak base salt. Being this kind of salt, there's going to be more acidity left over, right? So that makes this salt acidic. We're talking about some kind of acid-base reaction, right? Because we got acid, which is acidic salt, reacting with the base. So that is why pH goes down. So this concept of strong acid weak base or weak acid strong base salt. So I want you guys to pay special attention to this particular topic, because later on in the second section of this chapter, we're going to discuss this, we're going to use it, and that'll explain so why we see the equivalent point or equivalence point with the various pH. And by the way, this salt problem could be one of the most mistaken problem for the students. Okay, so I just want to remind you, keep a good attention to this type of problem, the salt problem. All right, now, one of the direct application for the common ion effect is the buffer solution. According to the buffer solution, so that is a solution that resists the change in pH on addition of both acids and bases. Well, this seems a little bit too much for us to understand, so let's put this definition of buffer solution this way. Buffer solution is a solution contains a weak acid and its conjugate base. Since we see the pair of conjugates, so the buffer solution actually is the practice of common ion effect. So here I try to tell you that all the buffer solution is an example of common ion effect. Vice versa is not true. Okay, so common ion effect does not happen to be a buffer solution. But buffer solution is an example of a common ion effect. That is always true. So that means we can set up an ice table for buffer solution for whatever the problem that we're going to see. But here, what I'm about to tell you is there's some kind of a shortcut that we can actually use for buffer solution without going through the ice table. Being a buffer solution, there's always been a mixture of a conjugate acid or base pair of a similar, relatively high concentration. So here I just want you guys to recognize high concentration. That is very important. Low concentration of these pair of conjugates are not what we called as buffer. One other thing, I almost forgot about here. Okay, I just think it. So here I want you guys to pay attention. Weak acid and its conjugate base. So weak acid, we understand It's a WA. Oh, so if we have a weak acid, what is its conjugate base? Is that going to be strong or weak? Yes, it's going to be weak. So for a buffer solution, that is solution of a pair of a weak acid and weak base as conjugate. It cannot be strong acid or strong base. Has to be weak acid and weak base as pair of conjugates. Okay, for a buffer solution, okay, the pH of this buffer solution should be very close to the pKa of acid that we choose. Since the pH value, as we understand, 3, 4, 5, 6, or whatever the value, so the higher the value of a pH, that means the lower value of Ka, the weaker the acid it is. So I just want you guys to remember, for a buffer solution, it is going to be weak acid and its conjugate. So there's a pair of weak acid and weak base. In order for us to figure out the pH of a buffer solution, we can actually derive from this base or acid dissociation of a weak acid from the Ka and from that equation, mathematical expression, but let's ignore all of that. Let's come to the conclusion directly. So the pH is equal to pK plus the log of concentration for Cb divided by the concentration of Ca. Cb stands for conjugated base, Ca stands for conjugated acid. And here I want you guys to realize we put EQ. Okay. We put the EQ as a subscript to let you guys to understand we talk about the equilibrium concentration here. Well, according to the math, oh, by the way, this is the equation we call the Henderson-Hasselbalch equation. This is the equation that Henderson and Hasselbalch found almost 200 years ago. Back then, we didn't have a pretty good idea about equilibrium in chemistry, so that is why this equation is widely used for biochemistry. As a matter of fact, it turned out it gives the birth of a mode of biochemistry. Okay. So if you get a chance to take a biochemistry later on, okay, this is about the first equation that you're going to see. Okay, so from that equation, HH equation, we realize we got the log of Cb over Ca. According to the math, if we multiply V top and the bottom, because V is going to cancel, right? So mathematically speaking, nothing's going to change. But in chemistry, it changes a lot. Remember, this Cb, so the square bracket means molarity, moles per liter. Multiply by the volume, that means moles. So another variation of HH equation is equal to pH equals to pKa plus the log of moles of conjugate base divided by the moles of conjugate acid at equilibrium. Sometimes you probably find out that this equation is more useful than its original version of HH equation. All right, so there's a more variation of HH equation for the buffer solution. Okay. This is what we got from our discussion from previous slide. So pH according to HH equation, so that's pKa plus the log of Cb over Ca at equilibrium. Now, let's look at this ice table. Okay. Remember, buffer solution is a case of common ion effect. Common ion effect can be solved by the ice table, right? So let's set up an ice table. So say if we have initial concentration with this pair of conjugates, This is a must of a buffer solution, right? So we say we know the initial concentration. And we can set up change and set up the rest of ice table. So this is what we have. So initial concentration for conjugate acid minus X, that will be the equilibrium concentration of Ca. And Cb initial plus X would be the equilibrium concentration for Cb, and the plus X would be the equilibrium concentration for hydronium. Say, okay, if we have a high concentration of this pair of conjugates, their initial concentration is so high, when they compare to the Ka, 500 rules applies. That means what? That means with the 500 rules, we can pretty much ignore those X terms. If we can ignore those X terms, initial concentration is equal to that of equilibrium for both the substances. In other words, we can replace this equilibrium concentration with the initial concentration. One other thing I'd like to discuss here about the 500 rules here. As we said before, initial concentration of pair of conjugates is very high. Remember, we talk about the weak acid and its weak base as conjugate. Weak acid, Ka must be quite small. If Ka is small, high concentration divided by the small value of Ka, so 500 rules is almost always applied for the buffer solution. So if that is true, that makes HH equation into this way. Why this version of HH equation is so important? Because it is the initial concentration. That means we do not have to calculate equilibrium concentration anymore for a buffer solution. So that makes our life a lot easier. So that is why HH equation becomes a shortcut for buffer solution calculation problems. In order to make this 500 rule works, we have a requirement for the Ka value. Remember, Ka must be small. So if a Ka is small, we can look at pKa. So pK must be somewhere between 3 and 11. So this is where the pH should be as a buffer solution, from 3 to 11. Again, if we multiply volume top and bottom in this division, so we can easily convert the molarity into the moles. So we have initial moles of Cb divided by initial moles of Ca. And you soon will find out this equation becomes more useful than the original version of HH equation itself. One other thing I'd like to discuss a little bit. Okay. For the buffer solution, it can tolerate a small change in volume by dilution. In other words, if we add a little bit of solvent or a little bit of some other things, okay, that's going to dilute the concentration of this buffer, but sometimes it makes no effect. Why it makes no effect? Here. Because most for conjugate base and conjugate acid is not going to change, even though we see the change in concentration. So that is why this equation in blue box is more important, more practical than this original format of this HH equation. Okay, so Just how are we going to calculate the math problems involving buffer solution? Remember, buffer solution is the application of a common ion effect. All right. Obviously, if a question gives us a word like a buffer, that's a whistleblower, right? So everybody should know it's a buffer solution problem. Or if a question asks for HH equation, Henderson-Hasselbalch equation, well, that's a buffer solution problem. But what happens if the first two are not mentioned? So how do we know it? Here's the clue. The concentrations of conjugated acid and base pair mentioned. This is more fundamental than the other two. The concentration of a pair of conjugates is mentioned. As a strategy, we identify this pair of conjugates. Okay? And with the concentrations known, most likely, so we can make sure that those two concentrations apply the 500 rules. Because once it's applied 500 rules, which is most likely it's going to satisfy, otherwise it wouldn't be called as buffer solution. So most of the time we see 500 rule applies. In this way, we can use initial concentration instead. Okay, so again, I want you guys to realize these are the initial concentrations. These are the initial moles. Okay. Why is that so important? Because later on, as we have a buffer solution with addition of strong acid and strong base added, it is a lot easier for us to calculate moles instead of a molarity. Once we get a moles from stoichiometry, boom, use that equation, second equation, we can get the pH out very quickly. So this is something that I'd like to mention here so that I can give you guys a heads up. If a 500 rules for some reason does not apply, okay, I stable that. There's no shortcut anymore. But I just want to, I'm not going to say guarantee, but most likely for a buffer solution, that's going to be a yes. But always check that out before you use HH equation. All right, so now let's look at this example problem. It says to use the Henderson-Hasselbalch equation to calculate the pH of a buffer solution that is 0.45 molar of ammonium chloride and 0.15 molar of ammonia. And we're given Kb of this ammonia. And there are so many clues, as you can see, about the type of calculation problem. First, Henderson-Hasselbalch equation. So that is one clue. If that clue is not obvious enough, here's the second clue, buffer solution. But what is more fundamental or more important for us to realize this problem, just in case none of these are asked, are the concentration of this pair of conjugates. NH4, NH3. This is a pair of conjugates. How do we know it? By the differentiation of one proton. Right? One more proton, conjugate acid. One less proton, conjugate base. So once we realize that there's a pair of conjugates with the concentration known, that is a buffer solution problem, period. All right. Now, let's talk about it. Okay, so here I will just explain just how we recognize the keywords for us determining the type of calculation problem. And of course, okay, handle HH equation, buffer solution, as well as those two concentrations of pair of conjugates, all of them leads to the buffer solution calculation problem. So we identify the pair of conjugates, We have a base, ammonium. We have acid, so ammonium, base, ammonia. And it's always a good idea to check the initial concentration of this pair of conjugates to see whether they apply 500 rules. Okay. Since it's a buffer solution, as I already mentioned, so we quite sure that 500 rules should apply. But we're going to try it out nevertheless. We have initial concentration of ammonia divided by Kb, and we find out it's going to be greater than 500. And we have initial concentration of ammonium, which is the same as the concentration of ammonium chloride, 0.5 molar, so definitely it's going to be greater than 500. So we can use initial concentration of ammonium as its equilibrium concentration. All right, if the answer is yes, as we find out, so we can use the HH equation. So pH equals to pKa plus log of initial concentration of Cb divided by initial concentration of Ca. But wait a minute. I just want to let you guys realize this is pKa. Do we have a pKa? No, we don't, because we have Kb. Okay. So pKa equals to 14 minus pKb. P means negative log, so we put a number in, take a negative log and subtract it from 14.00, so we got 9.26. All right, so now with the pKa known, initial concentrations are known, so we applied it to it, so we find that's 9.74, the pH of this buffer solution. All right, so now that we know how to use the HH equation for our buffer solution, and here I'd like to emphasize one more time, there are certain clues about the buffer solution calculation problem, like HH equation, like words of buffer solutions, or more importantly, we know or we see the concentrations of a pair of conjugates, weak acid and weak base, are mentioned somehow. So these are the keywords or the clues for us to realize the buffer solution in calculation. Okay. So why is buffer solution so important? So first we need to understand what the buffer really means. For a buffer solution, we must have high concentrations of both weak acid and weak base. Okay? And this pair must be a conjugated pair. How high the concentration? At least 0.1 molar in chemistry. Otherwise, we wouldn't call it a buffer solution. The key feature about the buffer solution is pH does not change that much if we add a small amount of a strong acid or strong base. In other words, pH is almost remains unchanged if the solution is being introduced by some strong acid and strong base. Small amount, it cannot be too big. If it's too big, it will destroy the buffer solution. And that is the most important feature about this buffer solution, because pH doesn't change much. Okay. You probably already know, and so we already discussed before. Okay, so brown bag syndrome. Okay. So if a person is in a panic attack and he or she needs a brown bag, so covers the mouth and the nose so that he or she can breathe in the carbon dioxide back into the body. Why is that so important? Because for a panic attack, the pH of our blood become more basic. So that is why we need carbon dioxide or more carbon dioxide by breathing in our own carbon dioxide into our bloodstream so that it will generate carbonic acid to lower down the pH, to reduce this panic attack syndrome So that is how important it is for pH to be stable in order to have our body functioning. Why? Why a buffer solution can keep pH basically unchanged? So here, I just want you guys to realize we got a pair of weak acid and weak base as conjugates. Remember, buffer solution is application of a common ion effect. So if we have a common ion effect, so say the common ion is conjugated base. When a small amount of acid or base added, first, the old equilibrium is disturbed, it's gone. So if we add a strong acid, say hydronium, it is the base, the conjugated base, that's going to react with this hydronium as a base reaction. And it's a strong acid, so the reaction goes 100%. That means the hydronium introduced by the strong acid is going to be gone. It's going to be gone by forming a weak acid. Remember, weak acid doesn't have too much of dissociation. So there's no much of a source of hydronium anymore after the reaction. pH is virtually changed. Virtually unchanged. Same reason, if we add strong base, let's say sodium hydroxide, now it is a conjugated acid in this buffer solution reacts with hydroxide. 100% for completion, so we got a conjugated base. Remember, it's a weak base. Does not give back too much of hydroxide, meaning hydroxide of this buffer solution doesn't change much. If the concentration of hydroxide doesn't change that much, pH is virtually unchanged. That explains why a buffer solution can cause the pH virtually unchanged when it is introduced to some small amount of a strong acid or strong base. According to the math, if we add a small amount of acid and base, so we have moles of this pair of conjugates changed after the reaction. So we should be able to get the moles because we can do that the calculations through stoichiometry. So once we have the new initial concentration of HA and its conjugated base, so we can use HH equation. Use HH equation, mathematically speaking, it doesn't change a lot of pH. So that's what the buffer solution is all about. So we can explain from chemistry and also we can explain from mathematics. Why a small amount? First, small amount of this weak acid and weak base does not necessarily change the volume, which is a good thing. Remember, if we change the volume too much, the concentration will change. The concentration will change, it will change the pH solution. So it virtually does not change the pH. In order for us to keep the 500 rule applies, we must keep this pair of conjugates in high concentration. So that is the reason why we cannot add too much of a hydronium or hydroxide, because if we add too much of these, we cannot keep the high concentration for either of this pair, either component of this pair. This buffer solution will be destroyed. So only a small amount. All right, so once we know just how the buffer solution works, when a small amount of strong acid or strong base is added, we can lay out the procedures for the calculation problem of a buffer solution with the addition of acid and base. In our course, when we introduce acid and base to a buffer solution, usually there are strong acid or strong base. So in order for us to realize this type of calculation problem, not only do we see the buffer solution, we also should be able to see a strong acid or strong base in the question. The strategy. Since this calculation talk about the reactions, reaction is in stoichiometry, so we need moles of everything in this reaction. At the very beginning, if we do not know the pH of this buffer solution, so we need to calculate the buffer solution. So we need to calculate the pH of this buffer solution. We check out whether this 500 rule applies. If yes, 500, so HH equation. If not, less than 500, so we have to solve it using IS table problem. But since it's a buffer solution, 500 rule usually applies, so HH equation should be fine. So with the HH equation, it means we can use the initial concentration instead of equilibrium ones for us to do the calculation. So once the pH of this buffer solution is known or is solved, what we need is to calculate the moles of the components of this pair of conjugates. We need to know the moles of weak acid and weak base before addition of acid and base. Then we need to know just how much in moles of this strong acid or strong base is added. Well, here, as you're probably going to see that in your homework assignment, or probably even worse, in your exam, and some polyprotic acid or base will be added. And if we have a polyprotic acid or base added, make sure that you apply stoichiometry for such acid base. For example, H2SO4. It's a diproduct. Diproduct meaning what? It means we're going to have twice as much of hydronium than acid itself. Okay, so stoichiometry of acid and base for strong polyprotic acid and base must be considered. All right, so now we're going to calculate the moles of this pair of conjugates during addition or after the addition. So if acid is added, remember, it is conjugated base becomes the reactant to react to eliminate the external or the more hydronium caused by the addition. So it's a base. So it's a base and it's an acid. So base as a reactant and acid as a product. Of course, as a product, we're going to see the amount increased. As for a reactant, we're going to see amount decrease. So this is how we understand which one is going to be addition, which one is going to be the result of subtraction. So as for a reactant, it's always a subtraction in between. And for the addition of a strong base, I just want you guys to understand now it is the weak acid that's going to be the reactant, and the conjugated base is going to be the product. So we're going to see the increase of concentration of conjugated base if OH minus is added because it's a product. So as for product, it's always a plus sign. So we're going to add the moles of hydroxide and the moles of conjugate base all together. And once we know the moles of this initial concentration of an acid and base after the addition, we use the HH equation to solve it. And of course, remember we have a variation of HH equation. There's a log of moles of Cp divided by moles of Ca. So that is why you see it's how convenient it is if we know the HH equation with this particular variation. Now, let's look at the third example problem of this topic. So this example basically covers pretty much everything that we have discussed about the buffer solution. So 3 different questions. First, we need to calculate the pH of this buffer solution. Second, we need to calculate pH of this buffer solution after a strong base is added. Third, we're going to calculate the pH of this buffer solution after the strong acid is added. Let's start with first question. For this first question, we see it has a buffer solution. As a matter of fact, we have a buffer solution for all 3 questions. Buffer solution gives us a clue that's strong enough for us to think about. We are going to use HH equation, as you probably already figured it out. All right. Remember, in order to calculate the pH of the buffer solution in question A, so we need to know which one is acid, which one is a base, because we need to know which one on the top, which one at the bottom for the division. And we're going to apply 500 rules to check out whether they apply, because if they apply, we can use the initial concentration instead to make our life much easier. All right, so both this weak acid and weak base as a conjugates has a concentration 0.5 molar divided by the Ka, so shown both greater than 500, so that's good enough. So for the HH equation, so we're going to use the initial concentration here. So with the initial concentration 0.5 divided by 0.5, so that's log of 1. Log of 1 has a value of 0, so it's just the pKa of this weak acid, so which is 4.74. Okay. I would like you to memorize 4.74 for the next few minutes, so that we'll see just how the buffer solution works if a small amount of acid and base added. All right, so now let's look at the second question. So we are about to calculate the pH of a buffer solution after 0.020 moles of solid sodium chloride is added. The volume of this buffer solution is 1.0 liter. While the volume becomes quite important information here. You're right, we need moles. Right? So we are giving the concentration. If we do not know the moles, if we do not know the liters, we're not going to get moles. So liters, or the volume of this buffer solution, must be provided before we go on for this type of calculation problem. All right, so from part A, we know the initial concentration of this pair of conjugates as a 0.50 molar for each. With 1 liter of solution, moles times 1 liter, right? So volume, so value doesn't change, but we're going to change the unit. So instead of molarity now, so we have moles. So we have initial moles of a weak acid, initial moles of its conjugates, 0.5 moles for each. Next step, we need to calculate as how much of OH minus or hydronium that's been introduced by the strong acid or strong base. So now we have a 0.020 moles of sodium hydroxide according to the question. And according to the formula, we realize it is 1-to-1 relation, right? So that is sodium plus OH minus. So this is a monoproduct. Monoproduct, that means the moles of hydroxide is going to be same as the sodium hydroxide after 100% of dissociation, of course. So we figure out the moles of OH minus from the strong base is 0.020 moles. All right, now we need to set up an equation. This setup is essential because if you set up wrong, we calculate wrong. We calculate wrong, we got a wrong pH. So that's going to cost us. So for the reaction with hydroxide introduced, so we understand hydroxide must be the reactant. Remember, it is an acid-base reaction, so weak acid that yields water and, as you said, salt, right? And of course, we use the net ionic equation format. So that is a pair of conjugates that we got here. And which one is this product? Base is the product. Acid is the reactant. Remember, product as the amount increases. So for the product, that's going to be a plus. For the reactant, that's going to be a minus. All right, so let's carry out the calculation. So moles of acid got decreased by 0.02 molar. By 0.02 moles. And the moles of conjugate base is increased by 0.02 moles, becomes 0.52 moles. Now that we have initial moles of this pair of conjugates, again, HH equation with a log of moles, plug them in, so we see it's a 4.77. 4.77, 4.74. That is pKa and the pH of this buffer solution. And we see, okay, we only talk about the difference of 0.03 unit of pH, meaning pH is virtually unchanged. So this is what the buffer solution is. Although we see the pH is still going to change, but not that much. And that is essential for us to keep a relatively stable pH for a lot of biological actions or activities. All right, as a third part of a question here, so we are going to calculate pH of the buffer solution if acetone acid is introduced. Again, we're going to calculate the moles of weak acid, weak base of this buffer solution before addition in 1 liter of solution. So now we understand it's going to be 0.50 moles for both. I'm sorry, for each of this component of the pair of conjugates. And we do not know the moles of H2SO4 directly from this question, but we are given concentration and volume. So we should be able to calculate the moles of H2SO4. We start with the 5.0 milliliter. We need the liters, so that liters can be cancelled from a molarity, so in order to get the moles. All right, so throughout the calculation, we found out it's 0.020 moles of H2SO4. I'd like to remind you, H2SO4 has 2 protons, so that is the reason why the moles of hydronium is doubled. It's a 0.040 moles because H2SO4 is diprotic. Diprotic means moles of hydronium is going to be twice as much of the acid itself. All right, so the solution has been introduced by the acetone acid. Now we realize base must be the reactant, weak acid must be the product. This is the pair of conjugates. So for the product, that's going to be the plus sign. I'm making a mess here, I'm sorry. And for the reactant, that's going to be the subtraction between the 2 moles of the conjugated base and the moles of hydronium, because that's reactant. Reactant, the amount has the amount consumed. All right, so for the weak acid, we add 0.040 moles. For the weak base, we subtract 0.040 moles. Now that we have the new moles of this pair of conjugates, we apply that to the pH with a variation of moles. We find out it's 4.67. That value shows we do see the change of pH, but not much. 4.74, 4.67, we talk about a change in the third digit of the pH. That's a lot. Okay. So pH is still, like we said, virtually unchanged. Because when we use a pH meter, 4.67, 4.74 is usually considered as the same because the last digit is uncertain, right? So it's a 4.7 plus minus certain degrees of the unit of pH. So that is the calculation of a buffer solution with acid and base added. And this is the calculation problem you're going to see in our exercise, in our homework assignment. Two things I'd like to address before we go into the last slide of this topic. First, we need to know which equation that we're going to apply in order to make acid and base reaction work, so that the hydronium or hydroxide introduced can be reacted. It is very important because if you got it wrong, we're going to calculate the moles wrong. Second, productivity of the acid and base. That is equally important. I cannot emphasize enough, okay, to pay good attention just what kind of strong acid or base is added to the solution, because that's definitely going to change the calculation. Last thing I'd like to talk about here is the capacity of a buffer. Okay, when we talk about the capacity, that is the ability to resist the pH change of the buffer solution. In order for us to have the best capacity of a buffer solution, first thing we need to know is there must have a high concentration of components of a buffer. Okay. The higher the concentration, the greater the capacity. Which means if we have more moles of this weak acid and weak base, they can react more hydronium or hydroxide that are being introduced. So that means the better the capacity. Second, for a given addition of hydronium hydroxide, the ratio of this pair of conjugates change less when those concentrations are similar than they are different. This is very difficult to understand. Okay, so let's put it in a different way. A buffer solution has the best capacity when the concentration of this pair of conjugates are the same. Okay. So the closer the concentrations are between this pair of conjugates, the better the capacity. And of course, if you have an equal concentration of this pair of conjugates, the log term is going to be 0. That means pH equal to pKa for this buffer solution. Remember, it is a pKa, and always pKa. Speaking of buffer range must be pKa plus minus 1. Remember, plus minus 1. So that means the range of buffer is 2 units of pH. 2 units of pH indicates we have a concentration of this pair of conjugates varied from 10 to 1 to 10. We will talk about changing the concentration by the fold of 100. So that's just how important it is for us to realize. If we change 1 unit of pH of our solution, we change the concentration ratio of the spherical conjugates by the factor of 10. So that is the reason why if we start off the ratio of concentration of this pair closer to 1, that will provide the best capacity of the buffer solution. That is all for the first topic of this chapter, buffer solution. And before we leave, I'd like to summarize a little bit about this buffer solution. Buffer solution is an application of a common ion effect. Common ion effect, of course, is the effect that can lead us to change the pH of the acid or the base solution. And since common ion effect has this particular function, so a buffer solution is being designed by nature or by a human being so that we can control the pH virtually unchanged if we have a small amount of acid or base added. The math part of this buffer solution has 2 types. First, pH of the buffer solution. The key words for us to realize this type of calculation is either the words of buffer solution or the words of HH equations, Henderson-Hasselbalch equation, or the initial concentrations of this pair of conjugates are mentioned. Those will give us a direction to determine whether HH equation is going to be used. And I'd like to have a few words about this HH equation. HH equation only applies, and again, only applies to the buffer solution. Okay? We cannot use the HH equation to anything else. HH equation only applies buffer solution. My experience tells me that some students later on will try to use the buffer so HH equation for all kinds of equilibrium, which is absolutely wrong. Remember, when you have the homework or take the exam, if you get the chemistry wrong, you're not going to get any credit, no matter how hard you try in the mathematics. So recognize a correct approach is a must for us to pass this class. So again, HH equation does not apply any other equilibrium problem. It only applies to the buffer solution. And last thing I'd like to address here is when we deal with the buffer solution with a strong acid or strong base added, we need to get a moles. And we need to take a pause for a few seconds to think just what kind of equation that can take care of this additional H3O plus or OH minus introduced. Which component of this buffer solution is going to take care of that? Because once this becomes the reactant, the amount of this component is going to be reduced. It's going to be decreased. And the other components are going to be increased. So this is how we can understand which one is going to be addition, which one is going to be subtraction for the calculation. All right. Thank you for your time, and I'm going to see you guys in the next section.